we're going to talk about the connection between monotonic functions and derivatives. When we say monotonic functions, we mean either increasing functions or decreasing functions. Let D be the domain of the function f. For any 2 points x and y in the domain D, where x is less than y, we call f a strictly increasing function if f of x is strictly less than f of y. But if we allow f of x to be equal to f of y, then we simply call f an increasing function. On the flip side, if f of x is greater than f of y, then f is a strictly decreasing function. And finally, if f of x is greater than or equal to f of y, we call f a decreasing function. This theorem shows us how to use the first derivative to test for monotonicity. Let's assume the function f is differentiable on an open interval I. From here, we can state 4 main properties. First, the first derivative of f is greater than or equal to 0 at every point in the open interval I if and only if f is an increasing function on that interval. Second, the first derivative of f is less than or equal to 0 at every point in I if and only if f is a decreasing function on I. Third, if the first derivative of f is strictly greater than 0 at every point in I, which means it can never be 0, then f is a strictly increasing function on I. And fourth, if the first derivative of f is strictly less than 0 at every point in I, meaning that it cannot equal 0, then f is a strictly decreasing function on I. Let's assume I is an interval from a to b. This means that I could be an open interval, a closed interval, or a half-open interval, just like you see on line 3. Now, when we talk about the interior of I, we mean taking the original interval I and stripping away its endpoints. Put simply, the interior of I is just the open interval from a to b. Let's assume that f is continuous on an arbitrary interval I and differentiable on the interior of I. From this, we get 4 key properties. The first one states that the first derivative of f is greater than or equal to 0 at every point in the interior of I, if and only if f is increasing on I. Here's how we can break this down. If the first derivative is greater than or equal to 0 everywhere in the interior of I, the previous theorem tells us that f is increasing on the interior of I, simply because the interior is an open interval. Then, by leveraging the continuity of f over the entire interval I, we can extend this to show that f is also increasing on I. On the flip side, if we assume that f is increasing on I to begin with, it naturally follows that f is increasing on its interior as well. So, by applying the previous theorem, the first derivative of f must be greater than or equal to 0 at every point in the interior of I. That completes the explanation for property 1. The second property says that the first derivative of f is less than or equal to 0 at every point in the interior of I, if and only if f is decreasing on I. We can explain this in the exact same way using the previous theorem. The third property says that if the first derivative of f is strictly greater than 0 at every point in the interior of I, which means it can never be 0, then f is a strictly increasing function on the interval I. The fourth property states that if the first derivative of f is strictly less than 0 at every point in the interior of I, meaning that it cannot equal 0, then f is a strictly decreasing function on I. Just like before, both of these properties can be fully explained using the previous theorem. These 2 properties on the screen are about the derivatives of constant functions. The first property says that if we assume that f is differentiable on an open interval I, then the first derivative of f is 0 at every point in the open interval I, if and only if f is a constant function on that open interval. The second property says that if f is continuous on an arbitrary interval I and differentiable on the interior of I, then the first derivative of f is 0 at every point in the interior of I, if and only if f is a constant function on I. We can easily get this second property by applying continuity to the first one. In this example, we need to determine the intervals where the function on the first line is increasing and where it is decreasing. We will use the first derivative on the second line to figure this out. First, we see that the first derivative of f is greater than 0 on the open interval from -1 to 0, and f is continuous on the closed interval from -1 to 0. So, by the previous theorem, f is strictly increasing on the closed interval from -1 to 0. Next, we notice that the first derivative of f is less than 0 on the open interval from 0 to 1, and f is continuous on the closed interval from 0 to 1. Therefore, using the previous theorem again, f is strictly decreasing on the closed interval from 0 to 1. Now, let's talk about the monotonicity of f of x equals 1 over x. As you can see on line 2, its first derivative is given, where x cannot be 0 naturally. It is pretty clear that this first derivative is strictly less than 0 everywhere except at x equals 0. So, based on the previous theorem, 1 over x is strictly decreasing on the interval from -infinity to 0, as well as on the interval from 0 to +infinity, which of course excludes x equals 0. In this example, we need to find where the function on line 1, which is defined on the closed interval from 0 to 2 pi, is increasing and where it is decreasing. First, let's find its first derivative, which is shown on line 1. Setting the derivative to 0 gives us x equals pi over 3 and 5 pi over 3. Because f is continuous on the closed interval from 0 to 2 pi, we can use the previous theorem to check the monotonicity on each subinterval. Since the first derivative of f is less than 0 on the open interval from 0 to pi over 3, and on the open interval from 5 pi over 3 to 2 pi, f is strictly decreasing on the closed interval from 0 to pi over 3, and on the closed interval from 5 pi over 3 to 2 pi. On the other hand, the first derivative is greater than 0 on the open interval from pi over 3 to 5 pi over 3, so f is strictly increasing on the closed interval from pi over 3 to 5 pi over 3.